Thank you. Thank you for all the kind words and my presentation. But yeah, today I'll be speaking in my own personal title, not associated to any company. And I wanted just to highlight some of the work that I've been doing together with many other researchers and engineers over the last like maybe 2-3 years. Some of them present here also in this group. So the title of the talk is Detection and Motion Forecasting for Self-Driving Vehicles. And as you'll see, I'll be covering a little bit the evolution, how this concept started, and some of the more recent developments. Let's get started. So first, I'll show the autonomy stack. Then I will present the task of detection and motion forecasting. Next, I will cover what is a base architecture for solving these tasks. I will follow with the recent extensions to the base architecture that significantly increase the baseline performance. Finally, I will wrap up with my thoughts. And if you have any questions, I think you were saying like maybe wait till the end of the presentation. I don't mind if I get to stop, so up to you, right? But yeah, let's go. So here is the autonomy stack, from sensor data all the way to the controls that command the vehicle. We start consuming sensor data, which can be from a diverse set of sensors: camera, LiDAR, radar, maps, microphone, etc. Then this is consumed by a detection module, which outputs all objects in the scene. Next, after a few cycles, generally at least 2, the tracking module is able to recover the internal motion state for each object. Then the motion forecasting module will estimate the future object states. This information is consumed by a planning module. Its goal is to produce ego states to take the vehicle to a desired location. Finally, this plan is consumed by a controls module that sends commands to the actual vehicle. This is the final execution. So in practice, here is an example of a scene with 3 cameras displayed at the top left and a bird's eye view visualization of the LiDAR point cloud, in this case colorized by Hive. You can identify, just by looking at it, a few cars, a few pedestrians from this view. So now the detection module aims to place polygons around all objects in the scene. In this example, you can see blue boxes for cars, yellow ones for pedestrians, and orange for bicyclists. After a few cycles, objects can then be tracked, and the internal state, such as position, velocity, acceleration, can be recovered. And you can see this indicated by these lines coming out from the objects. So I don't know how this will play back, but here is an example video. You can see all in action. You can see pedestrians and vehicles being tracked and their future motion estimates shown by the thin lines sticking out. And as you can see, this technique can be quite effective and work quite well. Now back to the stack. This approach is what most self-driving companies use, and it makes sense. It breaks down the problem into smaller pieces, and then every piece can be solved independently. However, it suffers from cascading errors. That means errors from earlier modules are very hard or sometimes impossible to recover later in the stage, and they start piling up. It also constrains the interfaces between the modules. In some cases, more information might be needed for proper motion forecasting. For instance, anticipation if a pedestrian will cross the street depends not only on the direction that she's walking, but what is she looking at? Is she paying attention to the road or looking at her cell phone? Also, context might be important. Like, is she in a bus stop, for instance? Is she in a bus stop? Perhaps moving, but waiting for the bus. Then in this case, might not be one to cross the street, right? This presents the question of, instead of trying to engineer these interfaces along with their, each module with their interfaces, what if some of these modules can be learned together? In this talk, I'll be talking about algorithms that attempt to solve all these 3 modules together. This approach has several advantages. It shares compute, potentially allowing for more efficient stacks, offers end-to-end learning, overcoming the cascading errors, allows for a wider interface between the modules, like more information is flowing through detection to tracking, for instance, and through tracking to motion forecasting. One of the successes of neural networks is that they learn their own internal representation. So in this case, the interface between detection, tracking, and motion forecasting is not only maybe wider, but is also learned by the neural network. So one potential downside of this method is that we have to deal with more complex modules. But then I'll be talking later about like some papers we published that try to help with this. Experimentally, we found that these techniques improve motion forecasting. They capture a higher dimensional object state. We will see motion forecasts that respect lane semantics, show real behaviors, like for instance, cars that slow down at intersections, as naturally human drivers do, and avoid other objects in the scene. So some things that with a simple interface as the one above are much harder, much more challenging to capture. So here is an example of an algorithm that combines all three tasks. You can see the detected objects in the scene as well as their future states. You can also see these models can estimate uncertainty shown by these ellipsoids, as well as multimodal forecasts. Let me pause here if I can. So there is a car, for instance, this, I don't know if you can see my mouse, but this car here could go straight or could actually make a right turn. Right? It's important to cover the two possibilities, and then these models are able to do that. This is an example of an algorithm that can do it. As this object more clearly starts turning, then the two modes collapse, and then the positive of going straight is very unlikely, so that it doesn't show here. So note that as I play this video, this is directly the output of one of the algorithms that we'll be seeing, and it's unfiltered. So you could imagine that this is easy to get just doing some temporal filtering, get a much nicer video of this. But I wanted to show the raw output of the model. So now allow me to introduce the task of detection and motion forecasting more formally. On the left, you can see a cartoon picture depicting the two tasks. In green is the ground truth or labels, which is used as supervision to the models. In blue, we show the output of the network. The task of detection consists on placing boxes for every object in the scene, typically vehicles, pedestrians, and bicyclists. The task of motion forecasting consists on predicting the future locations of all objects in the scene at some time horizons. You can see this shown here by some dots, right? As both tasks can be supervised with labels, the machine learning models have direct supervision to optimize both. On the right, you can see an example of the output. You can see the scene in Vallespi view with the LiDAR points and map information in gray. There are boxes for detected objects in blue, and the waypoints show the future locations of these objects at some time intervals. In terms of metrics, we'll be seeing mainly two metrics in this presentation. For detection, we use average precision, which combines recall and precision to evaluate the quality of the detections. This is very standard detection metric. And it is a value between 0 and 1, and the higher the better. For motion forecasting, we will use the average displacement error, which is the L2 norm of the difference between the predicted and the ground truth waypoints at future time intervals. You can see that on the picture on the right. Now, let me present a base architecture to solve these two tasks. Here are different modules of an architecture that solve these tasks, from sensor inputs all the way to the final outputs. So now I'll go step by step in the next slide to talk about each module. So LiDAR is one of the main sensors in most self-driving applications. Although today we have many variants, in this example, I wanted to show like a more typical one. It's an array of LiDAR sensors spinning in time and capturing range and intensity values at discrete locations. As you can see, the data capture can be assembled as an image, such that every line corresponds to one of the lasers, and every column is one of the measurements at a given time. Since this sensor spins multiple times per second, it is important to capture at least 2 full spins to have a chance to see each object twice at different times. You could alternatively use two different lidars to scanning at different times to get the same effect. This is required to get velocity. In practice, most algorithms will take more than 2 spins for robustness. Also multiple lidars, right? For capturing and also for capturing higher motion states, such as for instance acceleration. Next step is to stack features specific to each sensor before fusing together. Some methods use engineered feature extraction for early processing of point clouds, but many employ also a small network here. Next, there is an aggregation step, where all features from all modalities are aggregated together in a common frame. In a typical common frame used is Vallespi view. And that makes sense because it's kind of the output representation that we want. So most networks do this quite early in their processing. So all the information has to be assembled together in the same frame. An example of such a lattice is the one you can see in the picture of the right. where basically every pixel is one of the cells and contains all the information about that location. I would like to note that this projection step results in some data loss. So this is because there's quantization into the cell, and also multiple sensor readings could fall in the same location. So some sort of averaging needs to happen. Next, the network trunk extracts the features to solve these tasks. There are multiple choices for the trunk of the network. The most important part is to ensure that the features are being captured at multiple scales. Examples are cross scales and the picture shown here, but also FPNs, unique networks can accomplish that effectively. A complexity here is to find an optimal balance between real-time speed and network accuracy. Now, going to the task, we have detection loss and motion forecasting loss. For detection loss, we generally two components. First, we need to separate the objects from the road and other background elements, as well as determine its class. This segmentation is done by a classification loss. Most papers use cross-entropy or some variant of focal loss to deal with data imbalances. Then, for all locations that contain an object, the network has to estimate rotated rectangle that encloses the object. That is, for instance, the center, width, height, and orientation. This is done using regression loss, and typically optimized for the one or some sort of Hoover loss is good enough. For motion forecasting, we need to estimate the feature states of the objects in the scene. There are many formulations for this, but the most typical is to estimate the feature locations and orientations at discrete time horizons. For example, it is typical to use the time horizon of 3 seconds at 100 millisecond intervals. This would result in supervision of 30 waypoints for each object. A regression loss is used here, generally also L1 or Hoover loss. This architecture, given a history of LiDAR points, now is able to extract the information within the picture on the right. That is, all the objects in the scene and their future motion states. So now let's see a base architecture that solves this problem. So I'd like to start with with InterNet, which was published in 2018. This diagram reads from bottom to top. The model takes a history of LiDAR data and also map information, projects all the data from both sensors into bird's eye view, and proceeds for independent feature extraction for each modality. Then the features from both sensors are aggregated early, and the step of aggregation in this case is simply a concatenation, since both sensor modalities are in the same representation from the very beginning. Next, these aggregated features are sent to the backbone network that will extract a joint feature space. And on that feature space, there are two losses for the task of detection and regression, as you can see in the picture. So at the time of publication, this model showed that it could preserve excellent detection performance while performing the task of motion forecasting. You can see an example of the output of InterNet on the right, on this slide. It is able to find the objects in the scene, as well as predict their feature locations, shown here as dots. In this picture, every object has its own color, right? And in white is the ground. So you can see it can be quite accurate. So now let's see some extensions and some more modern algorithms that expand on this. More recently, multi-XNet is a significant extension, bringing quite a few improvements. For instance, the addition of an actor-centric stage for refinement of the motion forecasting. Also, the estimation of uncertainties. This can be seen in the right picture as blue shaded ellipsoids, as well as the addition of multimodality for motion forecasting. You can see in this example that we want to capture all likely paths the car could follow when crossing the intersection. In this case, it could be a straight left or right. Multimodality and uncertainty estimation are very important for self-driving applications in order to get a better coverage of the future motion states. The planner needs to reason about the different possibilities the actors could do, as well as the confidence on these estimations. Here's a more detailed algorithm of multi-XNet, reading from left to right. It takes as inputs maps and a history of LiDAR points, then again employs an early projection into bird's eye view and combines both LiDAR and map features. Then after the backbone, the tasks of detection and motion forecasting are performed. Essentially, the first part of the network, which is what we show here, is the same architecture as InterNet. It just has a few improvements in terms of from data augmentation and a more expensive trunk and feature structure. Then it starts with the difference. It takes the detections produced by this part of the network and takes rotated crops from the feature space. Finally, another network is used for the task of motion forecasting. This step brings a refinement in the task of motion forecasting. It adds the estimation of uncertainties and the estimation of multiple modalities. And you can see on the picture on the right how this looks like. So it's the difference between left and right. Let me go more in detail. This is, just a reminder, this is the output of the first stage. It uses unimodal regression loss, simply minimize the L1 loss on the average position of the predicted future waypoints. The actor-centric stage extends this loss adding multimodality. This is done by adding another component, a classification loss that first predicts the probability distribution over the object's possible future motions, that is, being stopped, left, right, or straight. Then for each one of the modes, there is a regression loss. For estimating the probability distribution over the different future motion states, multi-XNet uses focal loss. The regression loss for estimating the future waypoints is also changed. In this case, we want to estimate the uncertainties. In order to do this, multi-XNet minimizes the KL divergence of the motion predictions and the labels. The distribution uses a Laplacian that makes the KL diversion loss a little bit more complex. But the paper does an Laplacian study to show that it can provide much better estimate than when using a Gaussian distribution. Finally, with these changes in the motion forecasting loss, you can see the results in the picture on the right. All future motion states have their uncertainties. Also, some objects have multiple possible modes, such as the object at the intersection. All three modes are correctly predicted by MultiNet, like going left, right, and straight. So the paper shows an ablation on the contributions. We can see that the second stage brings about 10% performance improvement in the task of motion forecasting. We can also see the task of uncertainty estimation and multimodality does not reduce the detection or motion forecasting performance, which is great. So you can see that these come for free. And here are some qualitative results. In red is the label information, and in blue is the model prediction. Also, the top row contains the results of the base architecture. That is just detection and motion forecasting, but without the second stage. On the bottom is multi-XNet. We can see that the detections are basically the same between the two methods, and that's expected since the actor-centric stage is only used to refine motion forecasting. Also, we can see the effects of multimodality. See, for instance, on the left, the base architecture thinks the vehicle will continue going straight when in fact it's turning right. You can see this, like in fact it's turning right, but the network thinks it's going to go straight. Adding multimodality allows the network to recover the two possible modes. It also thinks it might be going straight, but has another mode that correctly predicts that in this case could be turning right. This starts showing the example of why multimodality is important for estimating future motion states. Finally, uncertainties cover well the cases where the predictions are not as accurate. And the paper does an extensive study to show that it's able to produce very well calibrated uncertainties. You can see the example here, right? In this case, again, another vehicle has two possible modes, could go straight or make a left turn. But the left turn is a little harder to predict correctly. So the labels think that it may be taking as not such a tight turn in this case. So it's a little off, but you can see the uncertainties cover well what the label would actually happen. So this is an important part. In all these examples, the label information is always well covered by one of the modes and the uncertainty spread from multi-XNet. So here is, again, a video of multi-XNet in action. You can see detection, motion forecast, uncertainties, and multimodalities all together. Again, this is completely unfiltered, so there's going to be some flicker. You could imagine adding some sort of temporal smoothing could help to ease the flickering. But you can see it can be quite accurate, and also can do this in a global way with the whole scene. So we have covered multi-XNet. Now let's see what happens when we add camera sensors to the network. Let me introduce LCMB. This stands for LiDAR Camera Multi-View Network. This is an extension to multi-XNet. architecture that brings two ideas. The processing of LiDAR point cloud in its native frame, that is the range view, and the addition of input camera information. So previous attempts to bring camera and LiDAR together have tried to project the camera information into bird's eye view so that they can merge with the LiDAR. This is like, imagine projecting an image into a ground plane. Obviously, this suffers from severe distortion and information loss. So these techniques, to compensate for that, use large networks to extract image features before the projection into bird's eye view. However, a more common natural technique is to fuse both sensors in range view. That is what the sensor fusion for joint 3D offset detection and semantic segmentation does. This comes from the realization that both LiDAR and camera collect data in polar coordinates, and the information can be assembled together in an image. You can see this depicted in the picture here, right? You have LiDAR and image. They are not so far together. If we warp the image, so it's projected in the LiDAR frame, I mean, there are some missing pixels, etc. But you can see that overall the image structure is well captured. It's not so much of a distortion. So the two frames are very close together. So since both sensors operate in the same view, fusing the two together causes minimal distortions, as you can see here. And with this technique, not only performs better than trying to project in bird's eye view, but it's also more efficient because a very small network for image processing is sufficient to obtain good results. Borrowing this idea, here is an actual solution presented in the LCMB paper. The task part is the same as LeaderNet, so this top one here, so I'm going to skip it. But let's focus now on the second part. One thing it adds is it takes the point cloud and also creates the range view representation. And adds the images, right? The images come from multiple cameras, not just one, and employs independent networks to process both the LiDAR on one side and the camera in some other. Those are very small networks. Then the camera information is being projected into the range view, into the LiDAR view. And at this point, the two can be fused and further feature extraction happens here. Again, that's a very small network. Then we take all these features and then merge them back with, project them into bird's eye view, and at this point, we merge them back with the other modalities. So bringing images into the model improves the detection performance of the smaller objects, such as pedestrians and bicyclists. As you can see here, sometimes by even more than 60%. Since vehicles are bigger, they are supported by more LiDAR points. So the addition of camera is not expected to give large gains, right? Nonetheless, overall detection for vehicles improves on average about 4%. Note that the improvements grow at range, as expected, since the camera has a much larger angular resolution than the LiDAR. LiDAR measurements become sparser, and the camera benefit is more pronounced, as you can see, up to 70% in some cases. As expected, we don't see any statistical improvement in motion forecasting tasks, since in this paper, we only add the latest image. So, but if we could expect improvement in motion forecasting if an array of images or sequence of images was added to the network using the same algorithm. Finally, note that the addition of the range view, that is when we remove the image part, also brings some improvements at all ranges. Of a special note, the bicyclist class improved by 18%. This highlights the benefit of bringing multiple views for feature extraction into one model. So it's not just the camera, but also the addition of other processes of range view of LiDAR in addition to bird's eye view adds improvements. Here are some qualitative results. On the top, you can see the image for context. The middle row is the LCMB output, and the bottom row is the baseline without multi-view or camera inputs. So generally, you can see what the improvements come from, right? You can see, like in this case, there are some occluded vehicles at some range, and then you can see how not having camera, which is the baseline, misses these objects, but with the addition of camera and range view, these objects are being recovered. Even more challenging, here there are two construction workers at range. These actually might be occluded slightly in the LiDAR view, but with the camera information, they can correctly recover. And even more challenging, in a further range, there is a biker here. You can see the zoom in. This is very hard to see just with that LiDAR alone. I'm not sure there are many LiDAR points here, and it's completely missed by the baseline, but with the camera, this can be recovered. So we have seen how the addition of camera information can boost detection performance. Now let's talk about motion forecasting. Here is another algorithm that uses radar information to boost motion forecasting. Allow me to introduce LeaderNet, which stands for LiDAR and Radar Network. LeaderNet is an extension to MUTA that adds the history of radar readings to the input of the network. Radar is a sensor that can measure range rate or radial velocities using the Doppler effect. This can be used to obtain better estimation of the object state. This paper goes over many details regarding the radar, which I strongly recommend to take a look if you're unfamiliar about how radar sensing works. I took a snapshot of the paper that covers the modification that this algorithm does over multi-XNet. But basically, it takes the history information of all radars available and projects them, each one, into a radius of influence in bird's eye view. Then adds another branch of sensor processing to the network, which is this one. And the rest of the network is mostly unmodified. The appendix also includes a very detailed description of the network. So you can see here the 3 branches. So multi-XNet would be just LiDAR and map. This paper adds the radar branch. And then there is some aggregation. Then it goes into the backbone, which uses cross-scales network to extract features. And this feature space goes into a final detection branch, so detection head that does the detections. From here, we can go back to the feature space, do cross for every actor, and add this actor-centric stage. Overall, the addition of radar adds about 10% improvement over the base architecture in the task of motion forecasting. And the performance improvement for moving vehicles is even bigger, by about 13%. The archived version of the paper does show many examples and brings the results to show the benefits of adding radar. Here you can see one of the examples. At the top, there is, like indicated by this arrow, there is a car leaving a parking spot. And due to just coming out of occlusion and having very few LiDAR points, the network without radar is confused about where this vehicle wants to go. You can see it's not sure if it's going to continue turning left or going back to the lane. It's completely unsure. But now with radar, which is the one on the bottom, with LeaderNet basically, the network is able to lock in velocity and acceleration much quicker in the first time this object is being seen, and can correctly collapse all the modalities and more confidently say that this object's intent is to continue on the right lane. Again, in the archived version, there is a strong variety of examples highlighted. I think there are maybe like 20, highlighting the benefit of using radar early in the network. Okay, I wanted to show many more examples, but due to the lack of time in this presentation, allow me just to highlight some other extensions that may be interesting. For instance, we have seen that as models take more sensors, the probability of failure increases. How do we make them more robust to sensor failures? This paper investigating the effect of sensor modalities in multi-sensor detection prediction models covers this aspect and offers simple yet effective solutions. So we also skip very quickly through the details of multimodality. But if you're curious, this paper, Multimodal Trajectory Predictions for Autonomous Driving Using Deep Convolution Networks, is a very interesting read. The actor-centric stage can be extended to reason about interactions between actors. In this paper, Convolution for Spatial Interaction Modeling compares graph neural networks with convolutional networks and compares their performance. Then generally, these networks output very reasonable motion forecasts. However, we want to ensure these motion forecasts obey physics. The paper, Temporary Continuous Probabilistic Prediction Using Polynomial Trajectory Parameterization, employs techniques to constrain the motion forecast to actor-specific motion models and make them aware of the motion forecast of other actors. And finally, the base architecture presented here can be evolved to more sophisticated ones that employ smarter techniques. And one example is this paper here, ND-FuseNet. This one fuses gradually the temporal information, but also mixes range view and bird's eye view at multiple stages, including not only the time, but also in the early processing, and obtains with these significantly better results. So let's recap. With this, we'll end the presentation. So we talk about the importance of solving for detection and motion forecasting together to avoid cascading errors and to benefit from end-to-end learning as well as sharing compute. We have also covered algorithms to combine in one network LiDAR, maps, radars, and cameras, and the benefits of using information learning. We discussed that the addition of multiple view representations can boost performance. I personally think that processing the sensors in their native view with minimal or no modifications at all before projecting into any view results in the best performance. We have also covered the importance of multimodality for motion forecasting as well as estimating uncertainties. These techniques more easily allow the network to achieve higher levels of recall in its predictions. This is very important for safety. And finally, we have covered the importance of having an actor-centric stage to further reason about the motion of each actor. And with this, thank you for listening and open to any questions.
Hi, Carlos. Nice to see you again. Yeah, so I think this presentation is very cool. And I want to ask a question about the overall system diagram that you presented. I think in the very first of your presentation.
Yeah.
So in that diagram, basically, you are trying to combine the perception and not the multi-axis one, but the overall one where you try to combine perception and motion forecasting together.
1 second. Let me see if I can. I think I lost what I was sharing. So. Okay, is this the diagram or the one with multi-XNet?
No, the very first one where you have two diagrams. The first one is to have separate perception and yeah, this one.
Okay.
Yeah. So my question is, if you take a step back and look at the whole picture, we will see that there are some small but important cases in self-driving that a single model might or might not be able to solve very well. So for example, when you drive in the city, maybe there are reversing vehicles, or maybe there are vehicles that try to parallel parking or things like that. In these complicated situations, how what can be done, or what has been done in this yellow box to solve these cases?
You can see, first of all, there are some extensions, right? For instance, in the case of making sure all the predictions have higher recall or interact with other objects, I posted at the end some extensions. But more concretely, you're asking about in my understanding is you're asking about cases that are not very common or not very well covered by data. For instance, we not see very often on the highway, let's say a car backing up, right? That doesn't happen very often. So how we solve for this? So in these cases, you can think about if you have some data, we've done some techniques of sampling. Not in this case specifically, but other cases, some modalities like doing a very sharp left or sharp right turns, then those happen sometimes. You have some data, you can do more sampling when you train the network, so the network can see more of these examples. If it's never been seen, then one other option could be add some simulated data. And there is some work on this too, right? So you can actually generate, simulate data for training and engineer scenes where some actors do some of these other behaviors and then add this to the training data. But at this point, you enter into the realm of using simulated data, which is not necessarily real for training, and the network has to be able to accommodate all these modalities. This is if you want to solve with one model. I think it would be probably better, and that's my personal opinion, to have multiple models or multiple checkers. So you have your main thing, which could be this one, with give you some outputs that hopefully give you a very high recall about what's happening. But sometimes it's going to make mistakes. So if you, for 2 or 3 frames, are seeing hey, the output of this is inconsistent with what I'm actually seeing, the detections continue to go in a different direction where the network thought they would be going, then you could just set up another system that either tries a more engineered way of tracking this, or we can call it paranoid, tries to see, okay, this is I need to slow down, pay more attention to this. I don't know what's going on, but consistently this model is giving wrong estimates. This is some idea. So it doesn't need to be necessarily just one model, but the intention here would be to have an end-to-end system that gives you kind of a good overall 99% performance, but you still need to cover for this 1%. And you need to increase that by adding more data, more simulated data, or outside this model, have other techniques that verify this model when this model is not correct, jump in and then give you other estimates.
I see. Yeah, thanks. I think this answer is very insightful.
Yeah, thanks for the question, anyway. That's my personal opinion, by the way, so that doesn't relate to any company or what other players are doing.
Hi, guys. Yeah, that's totally fine. I guess it's your own opinion is also very valuable. So I guess, yeah, by the way, thanks for the great presentation. So I also have a very quick question. Also for this particular figure that Shangxuan just asked. So here, I guess when you motivate your design of this detection and motion forecast, joint detection and motion forecasting, one of the things you talk about is the cascaded error that exists in the top branch, in the top pipeline, right? Because you have more modules basically. So here, because I'm also doing joint detection tracking forecasting on my own research, so it's really close. So I'm just having a question here about even in your current pipeline, the joint detection motion forecasting, what about if the detection fails, right? You have a false negative, then you still cannot forecast it very well, right? So so that means you still have this cascaded error here, even if it's trained jointly. You have an end-to-end training, you have the joint optimization, joint cost function, but the detection in the real world in inference time fails, you can still not forecast it. So that's the like
it doesn't I agree. So yeah. But that's not the type of cascading errors that we're seeing. Sometimes in more traditional pipelines, when you do detections, yeah, you have, let's say a park car, let's say, right? So you put up, they place boxes, right? And then in the next frame, you place another box. Let's assume it just gets both. But they are sometimes not exactly the same. They are a little off. So now you do into the more standard like association tracking pipeline, and that induces some velocity, right? That's an example of a failure because detections are not exactly perfect and frame to frame move, then tracking will add some error, right? Into this. These kind of things are recovered by this network because it's kind of like the whole thing is optimized into error. And even if the box flickers frame to frame, still the velocities are like, they don't get affected by this, for instance. That's an error that doesn't happen here. But yeah, you're right. If you miss a detection, this network can also miss detections. Yeah, then you have the same. You still need something else to recover, like to have some memory, at least for the flickering, for other problems. You still have some of the same problems. There's some problems by the way.
Yeah. So basically, you're saying, okay, it's robust to some kind of flickering or some kind of inaccurate detection. But as long as you can detect it, you can kind of resolve the problem to some extent. But if you cannot detect it anyway, then the cascaded problem still exists.
That one is not cascaded at this point. It's just an end-to-end. So you optimize end-to-end. Yeah. So it's just simply like the end-to-end system missed that detection. It's not cascaded, but sure, some problems are still. I mean, it's not immune to any problems. It has some errors. Yeah. It's just some things are optimized end-to-end, and then you don't have some of the intermediate problems you have with this pipeline. But that's only one of the benefits. I mean, think about the interfaces. When you design the interface above, you have to say what detection sends to tracking. Are you going to send boxes? Are you going to send also like some velocity estimates? Are you going to send other features like the appearance to help tracking? What do you do there, right? Yeah. On the bottom, first, you don't do that design. You just put some layer. You design it differently. You set some layers and let the network pick its own representation. You don't have to engineer this. Sometimes by engineering these interfaces above has this problem that you may be missing something. You're just making a decision, and that adds a bottleneck. I think that's another big advantage of going with the band on the bottom. Right? You don't have to engineer this, and you can just put an arbitrary big bandwidth for features to pass through these interfaces.
Got it. Yeah, I guess that totally makes sense. And also, I think in the audience, there's also a follow-up question related to this. Basically, Andrew. He says that does joint network result in less yaw flip errors than a standalone detection module? Yeah, I guess that's for the detection. Can you see that question?
No, where do I go to see it?
It's in the chat. So basically in detection, you have these yaw flip errors, right? The front to the back, back to the front. So the orientation is totally wrong. I guess that's the question. So if you do joint detection and forecasting, will that help to reduce the yaw flip error?
I see. So yeah, I'm not sure this type of architecture will necessarily result in less flip errors. It depends, right? It's just going to look at the past history of observations. So during the transition stage, I think it might be possible. I mean, let's say you give like the last second of data. That's about the LiDAR spins 10 times per second. That's about 10 sweeps. And then the network has to reason about all these 10 sweeps and then put this information together. It is possible still sometimes gets confused about when somebody, like some actor, is flipping direction. We see it with pedestrians all the time, and sometimes when they stop and change direction, you start seeing like sometimes the things still continue to go straight, sometimes go. So there is that some of that flickering happen. The one nice part, and then at this point is the part of the uncertainty, is that the uncertainty ball increases because the network is unsure. So I would say in these cases, this is why it's important to estimate uncertainties. Is great because as this increases, that's an area that the planner needs to reason about. Okay, I don't know if the pressure is going to go here, here, or here. You know, that's this big ball. So now I need to slow down or even stop because I may be colliding with this pedestrian. That's one way, potential way that can mitigate this. But still, when something is like changing direction rapidly or something, I've seen errors of these end-to-end methods too. I don't recall if we've done the analysis to see which one fails more often. So I cannot comment on that. But yeah, that's a good question. Thank you.